Okay, so in this video, I'll extend my discussion of noise and offset to some other structures. As we have seen the calculation of noise and offset for the 5 pack or 5 transistor OTA, today I'll analyze these things for a bigger structure because they may ask some different structures which are not conventional. Overall, we should have the understanding that what is the contribution of every transistor at the output noise and how to refer it to the input. And if there are more transistors, what we have analyzed in the 5 pack, okay. So what we have analyzed in the 5 pack, then we have analyzed the contribution of this current pair and the contribution of this input devices. Okay, so we have analyzed the contribution of these four devices to the output and also of course M naught. But here in this video, we will see that what is the contribution of these Cascode devices. So for that, I'll explain the concept of what is the contribution of these Cascode devices. For that, I'll separately take the Cascode device. Okay. So yeah. So if we take the Cascode device separately, then we can see here, or no need to take the separately them. But yes, these are the Cascode devices. M32, M32, M6 are our Cascode devices in this structure. So simply the contribution of Cascode device is calculated by just considering the sources, noise sources of these devices individually. Okay, so if I consider this M3, okay, M4, just this is my 3, this is 4, and from the noise perspective we can see here input is shorted to ground for this input pair. Okay, so I am not concerned about them not. Okay, so what do we see here? We are seeing that this is my mirror is there, so I'm not drawing it because we want to see the effect of NMOS only. Okay, first we will see the effect of NMOS cascode. Similarly, we can extend this concept to PMOS cascode as well. So okay, this is bias point, so it can be shorted to ground. Now I will consider the noise source. This is the noise source that we are considering here. Okay, anyway, I am giving this direction, so this is my IN3 average. So we have to see that what is the contribution of this noise source at the output. I want to calculate the ISC n root 2 device third. Here third, not in the 5 pack, that is a different device. So this here 3 and 4 are the Cascode device. Okay, so we have to analyze this thing. How can I break this source so that we can analyze what amount of current is coming from upper side and what amount of current is going down side, so that we can calculate exactly the contribution at the output noise current. So I will apply one concept that if there is a current source like this, if there is a current source like this, and it can be split into two parts like this. I. So it can be simply like written like this, provided that this if this voltage midpoint is grounded, it means no current is flowing through this. So I is continuously going from here to there. So anyway, any current source can be written like this. So I will write this noise voltage like this. Sorry, noise current. So what we'll do, we will separately split this source into two parts. One part is this. So if I consider the direction downward, it means what? Some current is coming here, coming out of this, which is nothing but IN3, and the same current is going inside, which is again IN3. Same thing which I have explained here on the right. So now we have to see individual. If I am seeing the only effect of the upper current source, then we will see that this side impedance is 1 by gm and this side is a higher impedance. So I can roughly say that my complete current is coming from the upper side. So I can roughly say that my complete current is coming from the upper side. I will remove this. Just I want to show the direction. Okay. So this complete current is coming from this side, which is IN3, and this IN3 is copied here, IN3. Now if I consider only this lower current source, and what you will see, this side is higher impedance, this side is 1 by gm impedance. So overall I can say my entire current is going upper side. So you can see here my entire current is going upper side, which is nothing but IN3. So overall what you will see here, the current is copied here is IN3. So hence net current is 0. So overall we can see that this cascode device is not contributing to any noise current. So it means where this current is actually going, this current is going nowhere, but it is inside this device only. So this current is revolving inside this M3 device only. Whatever the noise current we have considered here as source, it is just revolving inside this transistor only. Okay, this is my M3. It is revolving inside this. The same story repeats for M4. So due to the M4 also, the short circuit noise current due to M4 is also 0. So what is the overall noise current due to M3 and M4? We are getting 0. So the conclusion from is that cascode devices don't contribute to the noise at the output. So same thing is true for PMOS also. Same thing is true for PMOS cascode as well. So ISC N3 equal to 0 means contribution at output, ISC N4 equal to 0. Same for ISC N 3, 4, 5, 6, 5 equal to 0, and ISC N 7, sorry, not 7, it is 5, 6. Okay. Now if I extend the same concept for the offset, then we can see here, if I consider any cascode device and we want to calculate the effect of offset, so just I am taking this M3 only, M3 M4 pair. This is my M3 M4 pair of my this cascode structure or means telescopic structure. One, two, okay, sorry, this is some VV naught, it is not 0. If these input are shorted and there is a, I'm not considering the VT mismatch of 1 and 2 here, which is already discussed in a 5 transistor OT offset. So here is the active load, which I will call mirror, okay, okay. So if I want to see the output short circuit current due to this mismatch, so I told this thing previously that we can model this mismatch. We can model this mismatch here as a voltage source, del VT. Okay. So due to this mismatch, what will happen? As of now, we can see that there is a no voltage applied at the inputs of transistor 1 and 2. So everything is settled. It means this VT mismatch will create a current. Let's suppose it is generating a current this side, which is nothing but GM4 del VT. So no current will come from this side. Let I consider this all the situation at rest apart from this VT mismatch. So overall I can see that this is nothing but GM4 del VT. So what we'll see here, yeah, this is a GM4 equal to GM3. So it is same like it is a short circuit current that we are getting at the output is nothing but GM3,4 del VT. So it is contributing to output offset, but actually its effect at input will be negligible. So we can see here that the effect of input referred offset will be negligible because of this. Why? Because what is the output short circuit current is divided by this, the input pair means input pair transconductance. So what the point is that exactly this GM is not a GM4. I will mention it as GM dash. So here I will write GM dash because the GM of this device is what? For this current pair device. So this is my M3 that we have to see, and this is my M1. This is my virtual short. That this point is virtual short. Okay. So what we can see here, this device M3 has the GM, which is exactly okay I out. So this GM3 is not exactly the GM3 that I am writing here. That's why I have written there GM3 dash. If this is giving me the RDS, then what is this structure can be written like this. So overall effect of this GM of this M3 transistor is written like this, M3. So what is the GM3? Actually GM3 I can write here exactly GM3 divided by 1 plus RDS 1 GM3. Okay. So here this ISCN is nothing but GM3 divided by 1 plus RDS 1 GM3 del VT. So from here we can see that the effect of this VT mismatch of Cascode devices 3, 4 is negligible. If I consider that GM3 RDS 1 is much greater than the 1, then this output short circuit current is nothing but 1 upon RDS 1 to del VT. So RDS 1 is of some higher order resistance, so we can see its effect is negligible or it is going to nearly 0. And also the input referred offset due to this device will be what? this device pair, the input referred offset voltage will be what? The short circuit current divided by GM of the input pair, or can say GM of the complete distribution, which is nothing but a GM of input pair. GM of input pair. So it is giving me del Vt divided by GM1 to RDS1, which is nearly contributed to negligible amount, that is I can say 0. So from this discussion we can conclude that contribution in offset due to Cascode device is also negligible. Same for PMOS, also true for PMOS Cascode devices. So what is the amount we are getting due to this? Input referred offset due to devices 3 and 4 is what? Due to devices 3 and 4 mismatch is what? 1 upon GM12 RDS 12 comma del Vt. So it is nearly 0, I can compute it. And similarly VOS of at input due to mismatch in 5-6 devices 5-6 is what? 1 upon GM12 RDS of the upper devices. The upper devices RDS is what? Okay, we'll see here. So here the RDS of 1 was considered GM dash is RDS. Okay, so RDS of 7 8 to del Vt of 5 6. Here I will write del Vt of 3 4. So it is also nearly come to 0, negligible. So this way we can see. So in telescopic structure also, as well, we have same specs of or same values of or same values of noise and offset. So this thing we can keep in mind in further discussion. Wherever the Cascode devices are coming, we will see that they are contributing to no offset and no noise. So this is the good point of the Cascode devices. So I think I have covered my discussion of noise and offset contribution due to these Cascode devices. So this structure can also be analyzed, Cascode. Any other structure where we are seeing the Cascode devices, we can directly say that there is a no contribution of these two devices, noise and Vt mismatch or offset at the output. So means there is a no input referred offset and noise due to the Cascode devices. So we are relaxed on these devices. So we are relaxed on these devices, noise and offset contribution. I think this is enough for this video. Later we will see, we will enter to the frequency analysis of 5 transistor OTA, where we will extend more concepts. And this is enough for this video. Thank you.